So our next speaker is David Evans from Cardiff, and he's going to tell us about the search for exotic conformal field series. Let's welcome David.
Okay, thanks. So I'm going to talk about a joint program with Terry Gannon in Alberta on the search for exotic conformal field theories beyond what you normally think of in terms of those arising from loop groups or quantum doubles, which for this talk I would regard as classical. So we want something beyond that. So it's also in some sense something beyond ADE. So eventually I'll give a brief summary of subfactor theory, because that's the prism or the framework I'm going to look through. But before that, I'll just remind you about what we mean by Valinda ring in conformal field theories. So this describes the representation theory of a loop group in terms of modules or representations, and that there's two standard pictures, one in terms of vertex operator algebras, which was really the context of the last talk by Timothy. And there's another context, which is exponentiating those Lie algebraic things to get conformal nets of von Neumann algebras. So these are essentially equivalent pictures, except that conformal nets are inherently unitary, whereas vertex operator algebras do not need to be unitary. So these provide us with, I guess, things we're not supposed to talk about, these categories. So say for a finite group G, you've got the representation ring, or for the loop group of, say, some compact group like SU2 at level K. These are categories, that they're objects, the representations, and then they're intertwiners, the morphisms. But there's more than that. You can multiply them so that they're actually tensor categories with a trivial object, the identity. And there's even more than that. There's intertwiners between products in different orders, which we denote by these braiding operations. So for say a finite group G, the representation ring, there's a trivial braiding. If you do it twice, you get back what you start with. So these two pictures here representing the morphism and its inverse are the same. But for the representation ring of a loop group, these are inherently different. If I do it twice, I don't get back what I start with. These are non-degenerate braidings, in the sense that these two are the same for a fixed lambda and all mu, only for the trivial object. So what we get from the loop groups are modular tensor categories with representations of SL2Z coming from these braidings. And so we have tensor categories, and then the problem I want to look at is, if you're given an abstract tensor category, not necessarily coming from these loop groups, is it the representation theory of something which describes an underlying conformal field theory? And so we're going to look at some examples coming from subfactor theory and von Neumann algebras, which throw out candidates for exotic conformal field theories, and then we're going to try and understand them and analyze them. So for that, I need to say something about factors and subfactors. So we'll start with some examples of factors. So we'll just look at infinite tensor products of, say, 2 by 2 matrices. Now, I want to think in terms of von Neumann algebras, which are going to be weakly closed on some Hilbert spaces. So I've got to represent them on some Hilbert spaces. And the simplest way is to take an infinite tensor product of representations of M2 on some Hilbert spaces H2. and then complete under the weak operator topology on this Hilbert space. Now, it looks as if there are lots of choices here, but in practice, there are very few factors that you can construct in this way. And they've been completely classified essentially by Kohn with help from Hogerup and going back to work of Murray and von Neumann about 70 years ago. So Vaughan Jones started the theory of subfactors, and you can think of them as follows. Suppose I have a group G, say a finite group G acting on one of these algebras, and then I take the fixed point algebra. Now, if the action is outer, I can actually recover the group G and the action just from the inclusion. So M is essentially unique and MG is isomorphic to M. So all the information is inside the inclusion. So these inclusions capture all the information of the group and the action. And so you're naturally led to want to study inclusions of these algebras as generalizations of classical symmetries. And then we think of the inclusion as being a quantum symmetry. Now, as I said, typically when I have these inclusions, unless it's completely trivial, these two algebras are going to be isomorphic. So there's an isomorphism of the big algebra onto the small algebra. And under some mild conditions, there's a dual object, an endomorphism from N into M. The dual, just as you think in terms of group representations, in that when you take the product, it contains the identity. So from these two objects, I can generate lots of endomorphisms between N and N and N and M and M and N and so on. But there's only 4 labels. I take all possible products involving rho and rho bar, decompose them into irreducible endomorphisms. And then we're only interested in the case where only finitely many things appear. So here's 2 examples. On the right-hand side, this is what you get when you have, when G is the symmetric group on 3 elements. So there are 6 elements of the group and 3 irreducibles. And this completely describes all the irreducible sectors that appear. And in the case of, this is another example which is related to E6. There are, again, only finitely many objects. These are the NN sectors. These are the NM ones. And the edges represent multiplication by rho. The nodes represent the irreducibles, the edges, multiplication by rho. So, of course, before looking at E6, one could also have looked at the A series for SU2, as in this example here. So the row at the bottom represents the NN endomorphisms. So these are endomorphisms on the algebra, the smaller algebra. And the second row, the upper row, are the endomorphisms between N and M. So I can only multiply the ones at the bottom. So strictly speaking, this is not the Valinder ring. For the Valinder ring, I'd want to be able to multiply all of these things together. So subfactor theory doesn't directly give me the Valinder ring. I have to do something extra. Because the Valinder ring, I have to use all of the vertices, say here for SU2 or for SU3. So this is for level K. I take the representation ring of SU2, which is generated by rho, which is this irreducible here. And then at level k, I want to kill off this representation up here, which is sk plus 1, this Chebyshev, essentially in terms of rho. So the Valinder ring, I need to be able to multiply all of them. So to do that, I have to do something extra. I have to look at representations of loop groups. So this was done by Anthony Wasserman. So now lambda is one of these vertices here, and I think of it as a representation, not just of SUN or SU2 in this case, but as a representation of the loop group. So pi lambda is a representation of the loops on SUN, but I restrict in this notation here to loops which live on an interval, a subinterval I of the circle. And I primed as the complement, and then the bicommutant, I just mean the von Neumann algebra generated by these loops, and the commutant here is those operators which commute with the representations on the complementary interval. And this gives me an inclusion of algebras. And they're actually of this very simple form here. If I take the vacuum representation lambda, this isn't a proper inclusion. It's an identity. It just defines me one algebra n. And then every other inclusion is isomorphic to an embedding of an algebra inside n given by an endomorphism. So this whole family of inclusions is described by a family of endomorphisms which satisfy the fusion rules for SUN. That was Wasserman's key result. So I can then represent my Valinder ring as endomorphisms of one single factor n, which is something more than what I did on the previous sheet. And so this leads to a notion of representations of conformal net of factors. I have a family of factors labeled by subintervals of the circle, and a notion of representation ring of these things. So then the problem I'm looking at, can we go beyond this and find conformal nets and representation rings which have nothing to do with loop groups? And that's the main thing I'm going to talk about. So before I do that, I just want to be a bit more concrete with what I mean by these fusion rings. So the simplest example of these A models is the Ising model with three irreducibles, identity, rho, and alpha. Now, these three represent endomorphisms. The edges mean multiplication by rho. So rho times the identity is rho, and rho times alpha is rho. But rho times rho squared is the sum of the nearest neighbors, which is this. And of course, that is what we have for the Ising model. And this can be generalized in a number of ways. One is by replacing this abelian group Z2 by other finite groups. So I replace one by alpha by the sum of the group elements. Or I could take multiplicities of the representation of rho, which appears here, which is the trivial case here. So that's one thing which Terry and I have done following some earlier work of Izumi. And if I just put in a finite group to replace alpha, 1 and alpha, I go back to my previous sheet. And then we ask whether, just as for the previous case for SU2, I can represent all these endomorphisms on the same algebra. In other words, if mu labels this node here, then mu squared should be the sum of the group elements, and mu g, mu should be fixed by g. So the question is then, that does this category exist? And that this was shown to be the case by Tambara and Yamagami only in the case when the group is abelian. And of course, in that case, these two graphs are the same. Now, except in the case when I've got Ising fusion rules, in other words, when the group is two elements, this system is not braided. So it cannot describe conformal field theory. But you can get a braided system by taking an orbifold, which is completely trivial in the Z2 case, where I identify a group element with its inverse. So here, if I take the cyclic group with 13 elements and identify G with its inverse, when I take the orbifold, I only need half of these here. The fixed point splits, but there are two extra twisted fields that appear. I'll come back to that later. And then what Terry and I could show is that these systems here, the orbifold ones, can be represented by conformal field theories. Now, that's not the most interesting example to look at. The primary example of interest is to do with the Hogerup subfactor. Now, the subfactors I talked about at the beginning, this A series from SU2, these describe the subfactors up to index 4. This is analogous to what happens for the Virasoro algebra with the discrete series with the central charge below 1 and the continuous one above 1. Now, so for subfactors, the critical point is 4, and it's what happens above 4 that's mysterious. Now, the first subfactor, which has only a finite number of irreducible sectors and is irreducible in a certain sense, was discovered by Hogerup. It occurs at this index value 5 plus root 13 over 2. And the two graphs that I had, the NN, NM systems and so on, look like this. Now, so that means that the 6 objects at the top have some fusion rules, which I've written down like this. So if I ignore this perturbation here, which is in blue, this describes exactly the fusion or the multiplication table of the symmetric group on 3 elements. So it's certainly not abelian, so it cannot be braided. Now, the Jones index, which is really the square of the norm of the adjacency matrices of these graphs, is better understood if I take its square root. If I take the square root of this Jones index, then as a function of lambda, it's multiplicative and additive. That means that I can replace in all these equations numerical values for dimensions. So d alpha has to be 1 because index is positive. And because the dimension is additive and multiplicative, I then get this relation. That's a quadratic. I solve this and I get this relation here. That's not quite the index. I have to add 1, which is how I get 5 plus root 13 over 2. So if you look at this graph here, there's a central point and 3 arms coming out. This can be generalized, and then we get bigger values than root 13 coming in the discriminant of this equation here. So, as I said, this whole group system here is not braided, so I cannot look for a conformal field theory directly, but I can take his quantum double, just as I can take the quantum double of a finite group. Now, in subfactor language, that looks like this. If I take this system of endomorphisms on N, then, but by results which are now a few decades old, that there exists a subfactor of this product such that if I take the inclusion iota, multiply it with its iota, with its dual, then not only do I have this diagonal decomposition in terms of the original sectors, but the AA system for this subfactor is a modular tensor category. So that's non-degeneratively braided, and if this kappa, if this chi here is just the action of a finite group, this recovers the construction of Drinfeld. So this is a subfactor way of getting a quantum double for the whole group. And then we can ask, is there an underlying conformal field theory? So what Terry and I did was understand the modular data for the whole group. Now, the whole group was constructed in a number of ways. The first was by Ufer himself, which was basically constructing by his bare hands 6J symbols for the original system. Now, there was a later construction by Izumi, which constructed the endomorphisms explicitly on a type 3 factor. But this was needed some numerical calculations, so it wasn't exact. And so that causes a problem when you go to look at the quantum double. So this expression here for the modular data, the quantum double, needed to go through this numerical data. Now the Verlinder formula for the fusion coefficients is in terms of the S matrix. So if you know S approximately or numerically, then because N has to be integral, you can get it exactly. Now, there are expressions for the S matrix in terms of the T matrix and the fusion coefficients and the diagonal row or the diagonal, the first row or the first column of the S matrix. Now, the first row is basically these the dimensions of the quantum double, which you can compute by Frobenius methods. And so if you know N exactly and S exactly, and the T elements are not hard to pin down because they have to be roots of unity, then you get these exact values for S. And so miraculously, you get these clean expressions for the S matrix in terms of these cyclic cyclotomic elements. Now, that already suggests a way of understanding this double, because on the one hand, the values that appear on the bottom right-hand corner are what you get for the modular data for SO13 at level 2. And this part, the top left-hand corner, is reminiscent for the modular data for the double of SO3. So this suggests that the whole group is not as exotic as what people suspected. So even though it's not possible yet to construct the whole group subfactor naturally, it looks as if the double has a natural understanding in terms of the symmetric group S3 and SO13 level 2. So more than that, we can construct character functions for this modular data. And here's one example for central charge 8. And there are two solutions. So that these transform exactly according to the S&T matrices I showed on the previous sheet. And again, there are 6 characters at the bottom and 6 at the top. And the 6 at the top transform or are closely related to the characters for the quantum double of the symmetric group S3 or the dihedral group. Now, how do we actually glue these two parts together, the symmetric group and the SO13 level 2? Now, we've changed our viewpoint a bit. And instead of thinking of S3 and SO13, which switched to 2 Tambara-Yamagami orbifals on Z13 and Z3 cross to Z3, which is why I had Z13 at the start. So I started with the Ising model, then I went to these Tambara-Yamagamis, which are really arising from Potts models for Z13 and Z3 cross Z13, Z3 cross Z3. So for Z3 cross, for Z13, there are, to get the irreducibles, these are the twisted fields. Then there are 13 objects. I have to throw away the trivial object and duplicate it. Then I'm left with 12. I identify them and I get half of that, that's 6. Similarly with Z3 cross Z3, there are 9 objects here. I throw 1 away. I split them into 2 and I get 4. So that's the picture for these 2 orbifolds, and their fusion rules look like this. So if I think of the orbifolds identifying these 2 fields in terms of twice cosines, I get these fusion rules. I get these twisted Tambara-Yamagami fusions. And then the double of the whole group looks like amalgamating these things. These 6 objects at the bottom come from Z13. The 4 at the top come from Z3 cross Z3. And the 2 black ones are now no longer Z2 fusion rules. Of course, I still have to have an identity, but the other one, well, when I multiply it, I get sigma minus squared. I get everything in sight. So that's the regular representation. So unlike SU2 or SUN, when I multiply 2 objects in this double, basically everything appears except for a few holes or some extra objects. So if I take the Z13 part, if I multiply them, I get the usual fusion rules for the Tambara-Yamagami orbifold, plus R minus is thrown in. I have to take away the identity because the identity can only appear when I multiply something by its conjugate. And then similarly for the Z3 cross Z3 part, I have this kind of supersymmetric holes appearing. Right, so that means that we really do have to understand Tambari-Yamagami orbifolds. So that's one thing we focused on. And this is a summary of our most recent results. So indeed, we can represent these Tambari-Yamagami duals of Potts models by conformal nets. And some partial results have also been obtained by Marcel Bischoff simultaneously. And also, we had some results for constructing conformal nets for twisted doubles, which are new. And some of these results also work for vertex operator algebras, but not entirely, because some things are still, basic things are still not known for vertex operator algebras, such as whether an orbifold of something sensible is also sensible. And this doesn't arise for conformal nets because of unitarity. Okay, so that's a summary of what I've talked about. The original paper is 10 years old, but these are two recent papers on Tambari-Yamagami and reconstruction. So I'll stop there.
Okay, thanks, David, for a very enlightening talk. Any questions? Okay, if not, let's thank David again for this very nice talk. Thank you.